Well, hello, and welcome back to another episode of Quantitative Bites. It's great to see you all. I hope you're all doing well. Just want to talk a little bit more about the discrete Fourier transform today. So in last week's episode, we introduced the discrete Fourier transform, and we talked a little bit, in terms at least of a broad overview, about how the discrete Fourier transform works. And then we went to look at how we could actually implement that in C++, how we could write code to implement the DFT, and we looked at some very simple examples of that. What I want to look at today is a topic related to that, which is the topic of windowing. And this is an approach to taking a small portion of our signal and so that we can look at the frequency content, not just across the whole signal, but just over small portions of it at a time, which can be useful. We're going to talk about that more in a moment once we go to the computer. As before, this video really is not intended to be any kind of a replacement for a textbook on digital signal processing or a proper DSP course or anything like that. We're really only talking about a broad overview that I hope will give at least enough of an idea of what's going on so that you might be able to go on to actually apply some of the techniques that we're talking about to some problems that you might have. I, as always, would stress that if you really want to understand more of the detail of what's going on, there are a great deal of very good resources out there on the web. Wikipedia is always a really good place to start, and I really would recommend having a look at that. As with the previous video, it really isn't my intention today to go into any great details about the mathematics of what we're looking at, although there is a great deal of maths behind it, which is very useful and very instructive, and in many cases I think really quite beautiful. We're not going to look at that today. Like I say, my focus with this video, and as with the last one, really is intended to be more on the practical implementation side of things, more than the theoretical, all of the theoretical background to it. Anyway, before we jump to the computer and have a look at what's going on with windowing, I just want to say, as always, that if you like this video, please remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future videos. I do try to post a video once a week. I don't always achieve it, but that's what I try to do. So if you subscribe, you don't have to miss anything. Anyway, let's jump over to the computer and let's have a look at windowing. Okay, so I just wanted to start today's video with a quick recap of what we talked about in the video last week, in the previous video, and the purpose of that video was very much just to introduce the discrete Fourier transform, and we talked very briefly about how the discrete Fourier transform works, starting from the more familiar equation for the discrete Fourier transform, which you can see on the screen here. And just to recap very briefly, I don't really intend to repeat the content of the previous video, but just to recap, we have our signal defined by small x of n, and we're multiplying that by this complex exponential term for a particular value of k, and then we're summing that over all of the values from small n equals 0 to big N minus 1, where big N is the number of samples that we have in our signal. And we can do that for as many values of k as we like, and k, strictly speaking, should be defined within the range also from 0 to big N minus 1. And we went on in the previous video to explain how this complex exponential term here can be expanded into these cosine and sine terms representing the real part and the imaginary part of a complex number, as you can see here. So instead of the complex exponential term, now we have the cosine of 2 pi over big N times k times n, which forms the real part, and minus j, which is the square root of minus 1, times the sine of 2 pi over n times k times n. And we see that what we're doing is simply multiplying each sample of our signal given by x of n by the corresponding samples of the cosine and sine terms for that particular value of n, and then we repeat that over all of the values of n and add everything up as we go, and that gives us our value of big X of k for that particular value of k. And in the previous video we talked a little bit more about what's actually going on there, and in particular we showed some visual examples which, simply to summarize, I want to show here. So we have here the equation for our Fourier transform, and I've colored the cosine and sine terms in purple and turquoise respectively, and we can see those plotted in the middle plot down here. And we looked at a particular test signal, x of n equals the cosine of 2 pi over big N times 3 times n. So of course this is going to exactly correspond to one of the Fourier terms. when k equals 3. And we looked at how we could manually calculate the values of big X of k for the first 6 values of k. And we showed these examples here where in the top plot we have our original signal in blue. In the middle plot we have the cosine and sine terms of the Fourier transform respectively, in this case for k equals 5, clearly showing that we have 5 cycles of each within the duration of the signal, which is what k equals 5 means. And then in the lower plot we have the result of the product of the signal in the top plot by the Fourier terms in the middle plot, which gives the product that we see here. And we went on to explain how if you sum over all of the values in this product, then you get the real and imaginary values for that particular value of k. And in the example that we show here with k equals 5, we see that both the purple and the turquoise plots here, which correspond to the cosine and sine terms in the Fourier transform, are symmetrical about y equals 0, so when we take the sum we're going to get values that are very close to 0. And we went on and we looked at that for the first 6 values of k between 0 and 5, and we calculated what the real and imaginary values and hence what the magnitudes would be of all of those resulting complex numbers. And we saw that when k equals 3, which of course exactly then matches our input signal, we get a real value of 0.499, an imaginary value of 0, and a magnitude of 0.499. And the values were pretty much 0 everywhere else, or at least very close to 0. And in that sense, we're able to see how the discrete Fourier transform is able to identify particular frequency components in the signal. So when the input signal is close to or exactly matches one of these components of terms in the Fourier transform, then we will get a high value, otherwise we get low values. And it's worth noting that the value we get here of nearly a half comes from taking the sum here and then dividing that by big N, the number of samples. So in the example that we looked at, we used a value for big N of 1,000, so 1,000 samples over the whole length of our signal. And so we're dividing the resulting sum of these product plots here by 1,000, which gives us the value of a half. Obviously, if we didn't do that, the value we would get would be around about 500. So that was it for a recap. What I want to go on to talk about today is windowing. Now, the discrete Fourier transform as it is, as we've just seen, is very good, but it takes the transform over an entire signal, and it relies on the assumption that our signal is stationary over its duration. And what I mean by stationary is that it doesn't contain time-varying frequency components, it doesn't have discontinuities or things like that. It is a continuous, a nice periodic signal. If, on the other hand, we have a signal that is more complicated, which is nearly always what happens in real life, we might want to look at how the frequency content of that signal changes over time. So suppose we had a recording of speech or something like that, for example. If we were to simply take the discrete Fourier transform of that signal, it would give us the overall spectral content, or a view of the overall frequency content of that signal, but it wouldn't tell us anything about when in that signal those particular frequency components occurred. And it might be quite useful, one can imagine various situations where it might be quite useful to be able to break a signal down into not just its frequency content, but also to get some information about when those particular frequencies occurred. Now, the most obvious way to go about doing that is to window the signal, which means simply to take a short portion of the signal and take the discrete Fourier transform of that short portion of the signal, and then take another small portion of the signal and take the DFT of that, and so on, and build those up as we go. However, doing that is actually a little bit more complicated than it might first appear, and that's really what I want to talk about today. So in order to illustrate this, I've defined a slightly different example signal here. So we're using it's basically the same, but at a different frequency. So if x of n is equals a cosine of 2 pi over big N times 10 times n. So in this case, now we have a value of k for our test signal of 10, which is going to give a higher frequency. And that just makes it a bit clearer for illustrating the things that we're going to go on to talk about. In the lower left plot here, we see a plot of our signal against time, or at least against a small value of n. I've plotted only the first 500 values of n. In reality, we defined big N as 1,000, so this is the signal actually spans 10 cycles over the range from n0 to 1,000, which means when we look at it plotted over just the first 500 samples, we of course see 5 cycles of the waveform. If we take the DFT of that signal using the process that we talked about in the previous video, then we get this result. Now, rather than writing out the values in a table, as I did before, what I've done now is produce this impulse plot, and I've plotted for the first 25 values of k the absolute value of big X of k for each value of k. So rather than simply plotting the size of the magnitude of the real term or the imaginary term, I've simply taken the magnitude of the whole complex number and we're plotting that. Now in this example we see that for k equals 10 we get this big spike, exactly as we would expect, because we know that is the frequency of our signal, that we defined our signal to have for a value of k is equal to 10. And we see in the DFT when k equals 10 we do indeed get this spike which has a magnitude of 500. And of course if we were to take that and divide it by big N, which is 1000, that would give a value of a half, which is the magnitude that we saw in the tables that we were looking at in the previous video. So to take a small portion of a signal, as we've just been talking about, the process that we follow is to simply multiply the signal by some kind of windowing function. And that's exactly what we're doing here. We have our signal x of n is with the cosine of 2 pi over big N times 10 times n, but now we're multiplying it by h of n, where h of n is our window function. In this case, for the most basic rectangular window, this is the most basic shape of window that you might think of, we simply define hn as shown here. So we set it equal to 1 when n is between 75 and 375 and 0 otherwise. Now those values I chose simply to give us 3 cycles of our input signal and to start and stop at the point where the input signal crosses the 0 axis. Kind of arbitrary, I just picked those because I think it looks nice for the purposes of the illustration. So if we were to take the discrete Fourier transform of this now short signal, this small portion of our signal, we might expect that we would get a similar result. After all, the signal itself is basically the same. It still has a value of k is equal to 10. It's still the same amplitude, so we would still expect to see a peak at k equals 10. Unfortunately, the situation in reality isn't that simple. The result we get of the DFT of this windowed signal is the graph that we see, the plot that we see here on the right, as before plotted for the values of k between 0 and 25, and showing on the y-axis the magnitude of the complex numbers values x of k for each value of k. Now what we do see is that we do still have a peak at k equals 10, clearly corresponding to the frequency of our original signal. But now, whereas before that peak was completely isolated and we didn't really have anything else, we now see that we have a significant number of other peaks around it, which is obviously going to be a problem if we were trying to, isolate different frequency components in a signal or something like that. Then clearly the presence of these other values is going to be an issue. And it's quite interesting to have a look at why this is happening, what is actually going on. What really helps to understand what's going on is to look at the Fourier transform of the window function itself. So here we have our window function h of n defined exactly as before, and this plot here in the lower left shows the window function on its own, exactly as we would expect. And here on the right now we have a plot of the discrete Fourier transform of only the window function. So there's no other signal involved. If we just take the DFT of the window function, this is the result that we get. So what we see is that this pattern of impulses here is similar to the pattern of impulses that we saw either side of where we expected the peak at k equals 10 to be in the previous plot. And this is really important, and actually this is part of the reason why simply applying a rectangular window such as this to a signal is not necessarily a good way to go. Okay, so if we consider the mathematics behind what's going on, we have our signal here, x of n, defined exactly as before as the cosine of 2 pi over big N times 10 times n. And we have the Fourier transform, or the discrete Fourier transform of our signal big X of k, defined using the standard formula. And over here we have the definition of our window function, h of n, defined exactly as before. And here we have big H of k, which is the Fourier transform of the window function on its own, okay, defined using the standard equation for the discrete Fourier transform. Now, the important result to understand what's really going on is the idea that the multiplication in the time domain is equivalent to convolution in the Fourier domain. Now, as I said before, it's not my intention to go into any great detail about any of these things. There are great resources out there on the web if you want to know more about where this relationship comes from or the mathematical proof behind it. Or indeed, if you're not familiar with the concept of convolution, then I really suggest it go and look that up. And I think it will become quite clear really what's going on here. My intention, as I said, with this video is really to present only a very broad overview. But anyway, what we have is that we're taking our signal x of n and we're multiplying it in the time domain by our window function h of n. So we have x of n times h of n, and that is the equivalent of taking the Fourier transform of the signal, big X of k, the discrete Fourier transform of the signal, and convolving that with the Fourier transform of the window function, big H of k. Okay? Now, this is really important to understanding why applying a window function to a signal leads to the kind of result that we see when we then go on to take the discrete Fourier transform of that. And if we look at this visually, I think it becomes more clear. So what we're doing is we're taking our original signal here, x of n, so that's plotted the first 500 samples of that here in the top left plot, and we're then multiplying that by our window function in the time domain, which we see here, okay? And then what we're saying is that that is exactly equivalent to taking the discrete Fourier transform of our signal, which we know looks like this, with the big peak at k equals 10, okay, and pretty much 0 everywhere else, as we saw before, and then performing the convolution of that with the discrete Fourier transform of our window function, which has this characteristic pattern that also we saw previously. And it doesn't take very much really just to have a look at this and to see, because this is an impulse, just a single impulse, essentially a delta function. And when we convolve that by this, what we're going to get is this pattern of impulses is going to be repeated on either side of this peak, which is why we get the result that we do in the discrete Fourier transform of the windowed signal. Okay, now, it's more useful when talking about window functions to look at power spectra, or to plot the power spectrum, rather than simply looking at the magnitude of the complex numbers of the discrete Fourier transform as I was doing before. So in this example, we're seeing the rectangular window exactly as we saw before applied to our test signal. And the plot on the right shows the power spectrum from that, resulting from taking the DFT. And then what we've done is computed the power spectrum by taking 10 times log to the base 10 of the square of the absolute value of each of the complex numbers for each value of k. And what we get when we do that is we have our main peak at k equals 10, exactly as we'd expect, which shows it being 0 dBs because we've normalized to the maximum value in the result. And we now see that we have these features here, which are called side lobes, and we see the level of those at minus 10 dBs. So that shows that for this case, for this particular window, we are getting side lobes at about 10 dBs below the main lobe, which is not really very much. And this illustrates quite clearly why it would be a problem, perhaps, to window a signal in this way using a simple rectangle window, at least a relatively short one like this, because it's going to make it quite difficult to differentiate between different frequency components. So the level of the side lobe means that if we had another frequency component close to this one, it's going to be very difficult to differentiate that from just being a side lobe. Okay, so it turns out that there's a whole host of different possible window functions that we can use, all of which have different properties in terms of side lobe height and main lobe width. And they all have their strengths and weaknesses depending on the precise nature of the problem that you're trying to solve. For me personally, I've always found that the hand window is particularly appealing. It's just for personal reasons. I don't have any necessarily scientific basis for that, but it's sort of always my go-to window, if you like, when I want to look at solving problems of this nature. It isn't going to be the right window function to use in every case. I do want to emphasize that, but I find it pretty useful across most cases that I've had to deal with so far. And it is going to be the basis of the last example that I'm going to show in this video today. Anyway, so the hand window is defined here. So we have first of all, we have our signal defined exactly as before. X of n is equal to the cosine 2 pi big N over times 10 times n multiplied by h of n, except now h of n is now defined as being a half times 1 minus the cosine of 2 pi n over big N h, where n runs between 0 and big N h. Now, I put NH here because the number of samples over which we're defining the hand window is going to be different, perhaps to the number of, or might be different to the number of samples over which we define our signal. If we're defining our signal as being quite long, let's say 1,000 samples, but we might only want to look at 300 samples at a time, we are then only going to define our hand window over a range of 300 samples, and then it's going to be 0 everywhere else. Okay, so we've used a different big N there for that, just to help illustrate that. Now, if we look at the plot of the hand window and the resulting signal, then we see how different it is from the rectangular window. So the plot here in orange, this is the result for the hand window, which you can clearly see has a very different shape to the rectangle window we looked at before. It's much smoother. And we see here in blue is the resulting signal. So we've taken our standard cosine waveform and we've multiplied that by this hand window, which gives us this signal. Now, this window is defined here to be exactly the same length as the rectangular window I defined before, with exactly the same start and end points. Okay, and we see indeed that we still have 3 cycles of our signal within the duration of the window, although obviously now the amplitude is significantly tapered at both sides. If we look at the power spectrum of that result, we immediately see how this differs from the result for the rectangular window that we were looking at before. We see that we still have a peak at k equals 10, which is exactly what we'd expect, because that is still the frequency of our input signal. But now we see that the side lobes are significantly lower. You see now here we have side lobes at around minus 30 dBs, which is substantially lower than the result that we got for the rectangular window. And indeed, it's quite instructive to look at these two examples side by side. So here in the left-hand column, we have the time domain plot of our signal windowed by the rectangle window and the resulting power spectrum at the bottom. And then in the right-hand column, we have here at the top and the time domain plot of our signal multiplied by the hand window and the resulting power spectrum here in the right-hand lower plot. And if we compare the two power spectra, we can immediately see the differences here. So whereas for the rectangular window we get side lobes of about minus 10 dBs, for the hand window we get side lobes of about minus 30 dBs, which is substantially better. So that we can see immediately that the hand window is going to be better than the rectangle window for allowing us to differentiate between closely spaced frequency components within our signal. And that brings about all sorts of various advantages, which we're going to talk more about later on in subsequent videos in this series. For now, that is pretty much everything that I want to cover about windowing, except, as I've said, there are a whole host of different window functions available. If you can look that up again, Wikipedia is a fantastic resource for information about that. And I've simply chosen to show examples of the rectangle window and the hand window, but as I say, there are many more, all defined by relatively simple, in most cases, functions, so they're not that difficult to implement. Okay, so that's really everything I wanted to talk about today. As I said at the beginning, really just aiming for a really light overview, hopefully enough to at least give enough of an idea of what's going on that it might be possible to use these techniques for something. As I said in the beginning, not intended to be any kind of a replacement for a full DSP course or a DSP textbook or anything like that. If enough people are interested, I may well consider going on in the future to look at making more videos on digital signal processing, and we could go and look at these things in more detail. Let me know in the comments below what you think, if that might be something you're interested in. If enough people say they might be interested in that, then that is something I will give some thought to doing, perhaps in the future. But for now, I think we've covered enough now with the DSP and with windowing that we can go on in the next video in this series, which may or may not be next week, I'm not sure at the moment. The next video in this series we're going to go on to look at using the techniques of the discrete Fourier transform with windowing to look at how we can do simple time frequency analysis of signals, to look at how frequency content of signals is changing over time, and also to have a look at some example areas where we might actually want to do that. Anyway, that really just leaves me to say thank you very much for watching. It's been a great deal of pleasure making this video, and I really hope you've enjoyed it too and got something useful out of it. If you've liked it, please remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future videos. Anyway, I really look forward to seeing you in the next video. Bye.